Hello and welcome. So we'll be looking at expression for bending stress, or you can say the derivation of bending equation or the derivation of flexural equation. So take note of all of this. All right. So this is a part of a beam under pure bending. So this is a part of being under pure bending, and we are considering two sections, which is section A and B and section C and D, and the two sections at a distance of what, ds, and within this beam we are considering layer. We take a small elemental layer there, which is what, EF, at a distance y from the what, from the neutral layer. All right, so immediately this load is applied on this beam, is going to deform into what we have here. Normally we are not going to have this part here, you understand. This is just the only part that we are going to have. So we now decide to complete this part, to let them meet at this point here, so to form a triangle there. All right, so and this point to this point here is going to be our radius, and you can see that the layer here has also deformed into what we have here, and this is our neutral axis. So the distance here from this point to this point is y. So from this point to this point too is y. All right, so for us to start the derivation, we are going to be considering layer EF. So let's consider layer EF. All right, so if you consider layer EF, you are going to observe that our EF is equals to ds. Our EF is equals to ds, and likewise our neutral layer NN is also equals to what, ds. All right, again you are going to observe that we said that our neutral layer NN and the N prime here, they remain unchanged. Do you understand? So we can therefore say that NN will be equals to N prime, and then they are both equals to what, ds. All right, so both of them will be equals to ds. All right, so the next thing we are going to consider is, if you look at this diagram carefully, you are going to observe that we have two arcs, and we have just this side and this side as our arc, but we are going to have two lengths of an arc. The first one is this one here. We have one length of an arc here, and then we have another length of an arc here. The first length of the arc there is the arc formed by our what, the neutral layer. This is the neutral axis, and the one formed by this other layer EF. So the first one, we are going to consider the length of an arc for our neutral layer. All right, so from mathematics we know that when we talk about the arc length, is nothing but what, radius multiplied by the angle sustained. All right, and here we have here to be our radius multiplied by what, the angle sustained here. So if we consider NN, so this will be equals to r theta. All right, because from this distance here to this point here is r, so the radius multiplied by the angle sustained, that is what, theta. All right, so don't forget that we have established that our NN is equals to N prime, which is also equals to what, ds. So it means that we can replace this N prime here to be what, to be ds, to be equals to r theta. All right, I believe we understand that. All right, so now again we can call this one our equation number one, but I don't want to have plenty equation here. Let's just follow it gently. All right, the next one we are going to consider another arc length here, which is the one of what? The one of E prime F prime. So E prime F prime, E prime and F prime will be equals to, now the total distance we said from this point to this point is y, and from this point to this point is r. So for us to consider the arc length, it's going to be the total distance upward, just like the height. So the total height is going to be the radius plus the what? The y here. So it's going to be r plus y multiplied by what? The angle sustained. So we are going to have r, that is the radius, plus y multiplied by theta. All right, so that is what we are going to have. All right, the next thing we are going to consider is the increase in length of layer EF. Increase in length. Of course, this layer here, EF, change from what we have here to what we have here. So the increase in length of this layer EF, so it's going to be EF. The increase in length is going to be E prime F prime, E prime F prime minus what? Minus EF. This E prime F prime minus EF that we have here. All right, this is increase in length. Take note, please. This is increase in length. All right, so you are going to observe that I don't know, let me just put something here to indicate increase in length. So you will not go and take this EF for EF here. So let's put length here. Increase in length. Please take note of that. All right. So this, if we now substitute all these parameters that we have now, we have our E prime F prime to be this, and our EF to be what? DS, right? But DS is equals to what? R theta. All right, so let's make this substitution. So we can say that the increase in length in EF will be equals to E prime F prime, which is what? R plus Y into theta minus our EF. Our EF is what? DS. But DS is equals to what? R theta. I hope we understand. So we can put R theta here. All right. So for you to continue with this, you are going to clear the bracket. So this will be equals to R theta plus Y theta minus R theta. All right. So this R theta will go with this R theta here. Then the increase in length of EF will be equals to what? Will be equals to Y theta. All right. So that is what we are going to have. All right. So the next thing we are going to consider is the strain in layer EF. We know that strain is equals to what? Increase in length all over what? The original length. We know that the increase in length of layer EF is equal to this. And what is the original length? The original length of this layer EF is what? EF. And our EF is equals to what? DS. And our DS is equals to what? R theta. So strain, which is denoted, the strain in this layer EF, which is denoted as this, sorry, it's too big. So the strain is equals to increase in length. Increase in length, which is Y theta. Increase in length I would have loved to write increase in length over original length, but please, I want you to follow this closely. Maybe you can just write it. I'm trying to manage my space. So increase in length is going to be y theta all over the original length. The original length of this layer EF is what? ds, but our ds is equals to what? R theta. So we are going to write R theta here. And if you agree with me, this will go with this. Then the strain is going to be what? Y over what? Over R. Alright, so that will be the strain. So the next thing we are going to consider here, from Hooke's law, we know that our Young modulus, which is denoted by capital letter E, is equals to what? Is equals to stress all over what? All over strain. Stress all over strain. Alright, so don't forget, we already know that our we are considering this Young modulus for what? Layer EF. Alright, so now we are going to substitute for our strain here. So we are going to have stress divided by strain, and our strain is what? Y all over what? All over R. So this is what we have, right? So we can further rewrite this to be in this form. So we can say that our E is going to be equals to stress all over Y R, so which is going to be stress multiplied by R all over what? All over Y, right? So now we can say that our Young modulus will be equals to stress multiplied by R all over what? Y. Alright, so stress all over what? All over R over Y. Alright, so here we can actually maneuver this. If we make our stress the subject here, that is the bending stress in a layer EF, if we make our stress the subject here, that is we are going to multiply through by the inverse of what we have here. So it means that our stress will be equals to the inverse of what we have is going to be Y all over R multiplied by what? Multiplied by E, right? So, and then we can further rewrite this as stress to be equals to E over R multiplied by Y. Alright, so you are going to note that this E over R is a constant number. So we can say that our stress here is directly proportional to what? To Y. Alright, so we can say that our bending stress is directly proportional to the distance from what? The distance from the neutral axis. Alright, so the next thing we are going to consider, a rectangular member. So we are going to consider the rectangular member, and we take some we'll do some mathematics, and then we are going to compare the equation we get there with what we have here to derive what we have. So I'm going to clean this part. So we are considering the cross section of a beam as a rectangular section, and we are considering a strip of this rectangular section, of which the area is dA, and at a distance y from the neutral axis, and here is the force that is acting on the strip. All right, so what we are going to be doing is we want to consider the force acting on this elemental strip that we are considering from this rectangular section. And how do we do that? We know that stress is equals to force over area. If we make force the subject, there's going to be what? Stress multiplied by what? By area. But the area we are considering here is what? is dA, because we are just considering just a strip from this rectangular section. That is just a small portion. All right, that is why it's going to be what? dA. All right, so from that formula we know that our force here is going to be what? dF. So it's going to be, instead of us to have force to be equals to stress multiplied by area, we are going to have dF to be equals to stress multiplied by what? Multiplied by dA. This formula is gotten from stress is equals to force over area. All right. So from here, we note that our stress, we have already gotten our stress to be what? E over what? R multiplied by what? Y. All right. So we are going to substitute that here. We are going to say our stress is equals to E all over R multiplied by Y. So if we substitute that here, our force acting on this string is going to be E all over R multiplied by Y multiplied by dA. I hope we understand that. All right. So the next thing we are going to do is we are going to take moment about the neutral axis. So if we take moment about this neutral axis, of course, it's going to be an also an elemental moment, that is dm. So we are going to take moment about this elemental about this neutral axis. So it's going to be what? It's going to be we are taking moment in this direction at a the distance from here to here is y. So it's going to be df multiplied by what? Y. So it means that if we take moment about the neutral axis, we are taking moment about the neutral axis, is going to be what? dm, because we are taking the moment of this strip. So it's going to be df multiplied by what? Multiplied by y. All right. So, but this is our df here. We are going to replace our df with everything that we have here. So we are going to say dm will be equal to, it's going to be equals to E all over R multiplied by Y multiplied by dA, then multiplied by Y. All right. So if you look at this carefully well, you are going to observe that Y multiplied by Y is Y squared. So we can therefore rewrite this as dm to be equals to E all over R multiplied by what? Multiplied by Y squared, then multiplied by what? dA. All right. So the next thing now is for us to consider the total moment of this beam about the neutral axis. So for us to do that, we are going to integrate this equation. So of course, if we integrate this equation, we are going to have this, and then we are going to have this. All right. So if you integrate the m, you are going to get m. So which is going to be equals to, we have established that this is constant. So we are going to have E all over R, then integration of Y squared dA. All right. So you are going to note that the integration of Y squared dA is nothing but moment of inertia. Sorry, please. All right. So it is nothing but a moment of inertia. So note that what we have here is nothing but a moment of inertia, which is what? Which is I. I is equals to integral of y squared dA. Please take note of that. So that is a second moment of our axis, or moment of inertia about the neutral axis. All right, so now it means we can replace what we have here with what? I. So it means that our moment will be equals to E all over R, then multiply by what? Multiply by I. All right, so here if we make ER the subject here, we are going to have our M over I to be equals to E all over what? All over R. All right, so it means that, all right, so now next thing I want to do is from our first equation here that we said stress is equals to what we have here, we can make E over R the subject here. If we make E over R the subject, E all over R will be equals to what? Stress over what? Over Y. All right, so now we said M over I is equals to what? E over R. So our E over R is also equals to what? Stress over Y. So we can also equate this to be equals to stress all over what? Y. So this equation here is known as the bending, it's known as the expression for bending stress or bending equation or Flexural equation. All right, so one after the other, our M here, it means the bending moment. It means the bending moment, and the unit can be Newton, millimeter or Newton meter. All right, so our I here is the second moment of is the second moment of inertia. Take note of that. And the unit can be it can be the millimeter, mm to the power of 4. Can be mm to the power of 4 or meter to the power of 4. And the next thing here is our E. This is our Young modulus. And our R here is known as what? The radius of curvature. Radius of curvature. Why this stress here can be denoted sometimes with they can put B here, telling you that is what? Bending stresses. Please take note of that. That is the bending stresses. Why our Y is nothing but what? Distance of the layer in which the bending is considered from the what? From the neutral axis. So take note of that. And the unit can be what? Mm, or it can be in what? In meter. All right, so this is how to derive this Flexural equation. I hope we understand all of this stuff. So stay tuned for more interesting part. Thank you.